Okay, so direct proportion. Now, when we're talking about direct proportion, we're really talking about the relationship that exists between two quantities where there is a constant ratio. Some of the examples that we've used in class have been kilometres per hour, where the number of kilometres you travel is constant based on the number of hours that you travel. Okay, so it's really important then to know that anything that's in direct proportion, when it gets graphed, ends up looking like a straight line, a linear equation, so to speak. So we end up with a graph where there is a constant. Okay, so we have our y-axis and we have our x-axis, and you'll notice that if I was a bit more careful with how I drew it, that our direct proportion goes exactly through the origin, this point right here. The origin is the spot that is on a Cartesian graph, the point that is at 0, 0. Okay, so at 0, 0, it is where the x and the y cross each other. And it makes sense, really, because if we're looking at kilometres per hour, well, if I travel for 0 hours, how many kilometres will I go? Well, I'll go 0 kilometres. All right, so it makes sense then that our line will go through that area of 0, 0, through the origin point. Okay, now, because it's a straight line, we know that the linear equation for a straight line is written as y is equal to mx plus c. Okay, now, mx plus c gives us some information when we are dealing with linear equations. The plus c part here is really about where your line crosses the y value. Okay, so if my line was here and it was crossing my y value, that would be what my plus c was. But because we're dealing with constant relationship where it goes through 0, that means that there never is a plus c. It just doesn't happen. The plus c is always 0 because the y-intercept is always 0. So that leaves us with y is equal to mx. And so as not to confuse direct proportion with our linear equations, we actually rewrite the m as well. Oh, by the way, that m is actually the value of the slope of our line. So we can still work that out, what that would be, but we don't call it m, right? So let's get rid of that. In direct proportion, we call that value k. The k here really stands for the constant of proportionality. So the k is the constant of proportionality. So in other words, it's like the ratio that exists between the x and the y value. And in fact, if we rewrite our equation, y equals kx, so that the k becomes the subject of our equation, it really becomes k is equal to y divided by x. Right? So if we have our value for y and we divide it by x, we get our constant of proportionality. Okay, very good. We understand that. It's important then that we end up with the right values on our right axes when we're drawing our graphs. Now, the y is always dependent on what happens to the x. So we can say that our y value is always the dependent value, whereas our x value is independent. Okay, so we have our dependent value and our independent value, and we can actually apply those to our graphs when we graph things. So if I was traveling for 3 hours at 50 kilometres an hour, then I would be able to graph that. to do that, I would use my equidistant scale across my axes like this, and I would be able to plot the points of my data. Now, it might mean I need to actually come up with a table. We often will draw a little table of information. They look like this, where we will have 2 rows of data. Our top line is always our X value. My lines aren't exactly straight, but it doesn't really matter for what I'm doing here. Okay, so this will be our X value, this will be our Y value. Knowing that our X value is our independent variable, I could say, well, what if I drive for 1 hour, or 2 hours, or 3 hours, or so on? So, my car is travelling at 50 kilometres per hour. So if my X is 1, I've driven for 1 hour, how many kilometres will I have done? I'll have done 50. If I travel for X is 2, where my hours are my X, that means I'll have travelled for 2 hours, which means in reality I'll have gone 100 kilometres. Okay, so once you have all your points that you can then plot, you go back to your graph, you say, well, this is 1 hour, 2 hours, 3 hours. I could say this is 50 kilometres, this is 100 kilometres, this is 150 kilometres. And of course, you would be able to label, you've got to label your graph and your axes. You'd say that this is kilometres travelled, this is hours travelled, right? And then you would plot these points. And it just so happens that I've drawn it probably close enough that these points would be just about plotted on that line anyway. You would, of course, and it's very difficult for me to actually write them in, but you would write in your points. This would be 350. This point here would be 100. This one would be 150. Okay? Now, the good thing about having a graph of our direct proportion is that we can extrapolate data from that. We could say, all right, well, if we've travelled, if this was like 200 and this was 250, if I only travelled 175 right here, well, how long does that take me? And I could, of course, you'd have drawn this using rulers. You would be able to get your ruler and you would be able to draw it straight to our line, and then you would be able to go straight down from that line, and you would see that, oh yeah, it's about 3¼ hours is what it took me to go that far. So direct proportion is very useful, and we will be able to explore its uses further.